Okay, here we go. We're going to answer some questions. I'm on page 606 in your book. So 11-6, the lesson, was about adding rational expressions or subtracting them with like denominators already. And as we've seen with rational expressions throughout chapter 11, they act like fractions, meaning if you have a common denominator, add it together, no problem. So I'm looking on page 606, and what we want to do here are add together some rational expressions, these fraction-like objects, that don't already have a common denominator. So first things first, we have to be able to come up with a common denominator. I'm going to look at the two examples, 1a and 1b, on page 606 to help us think through how to find these common denominators. We do it the same way we do with numbers, so take a look at something like example 1a, where we have these two expressions, 15 mb squared, m squared b cubed, so m squared b cubed, and then 18 mb squared. And the first thing we're going to do is factor these expressions, right? We're going to, in this case, since they're just monomials, do a prime factorization. So 15, of course, is 3 times 5, and then the m and the b, being variables, we can just leave them in exponential notation already. And then the 18 mb squared is going to be 2 times 3 squared times m times b squared. Anytime we're finding LCMs, we simply want to identify every individual factor we see. It does not make a difference whether they're repeated or not, whether they have them in common or not. Every individual factor we see to the greatest power we ever see it raised to. Not combining them, again, it doesn't matter if they're in common or not, but just the greatest individual power we see. So obviously the factors I see here, we've got 2, we've got 3, 5, m, and b. You'll notice where I'm underlining it is random, it makes no difference. I'm just noticing these are the individual factors I see. So I'm going to write down 2, 3, 5, m, and b. And I know the LCM is going to be the product of all of these. But like I said, it's the product of whatever the greatest power we ever use is. So for 2, even though we don't usually write it down, that would be 2 to the first. For 3, though, that's going to be 3 squared. I'm not combining them. I'm not saying 3 to the third because there is an extra 3 up there. Just picking the greatest power. M squared. The 5, whoops, skipped over that one, 5 to the first, right? Even though we don't write it, that's the power. And then, of course, the b cubed. And so it's that product that's going to be our overall LCM. In this particular case, that works out to 2 times 3 squared, that's 2 times 9 is 18, times 5 is 90, times the m squared, times the b cubed. And so that is our least common multiple. Now again, the reason the LCM, or the least common multiple, is important is that if these monomials were our two different denominators, to add together fractions with these denominators, this is the common multiple I would use, the least common denominator that I would end up using. For example, let's ignore the variables for a second. Let's just imagine it was something like the fraction 7 over 15 plus let's do 10 over 18. Well, 15 and 18, we've already seen their factorizations. 3 times 5 and 2 times 3 squared. We've already seen the LCM would have been the product of 2, 3, and 5 to their greatest powers. So again, I'm just ignoring the variables, but otherwise it's precisely the same. 2 to the first, 3 squared, and of course 5 to the first, which is 90. And so what I want to be able to express these fractions as is something over 90 plus something over 90 if I were adding them together, if these had been the denominators of fractions. Because this 15 is not 90, though, I need to say, well, I know it's going to be a factor of 90 because we just came up with the common multiple. What times the 15 would get me to the 90? And of course, what it ends up being are the missing factors. So obviously, I did not have a 2, but I was also missing one of the 3's. 2 times 3 is 6, and so it's actually 6 over 6, a form of 1, that would get me that common denominator, and that's why this would be 42 over 90. And then for the 18, I asked myself, well, what was I missing? And it was clearly the 5. And indeed, it's 5 times the 18 that gets you 90. But again, I can't change the fraction, so I'd be multiplying by a form of 1, 5 over 5. So that gets you 50 over 90. And then it's that sum that we're interested in simplified. So 92 over 90 ends up being the same thing as 46 over 45. So that's why we're coming up with these least common multiples, because they're going to help us with least common denominators, and then they're also going to help us in terms of figuring out what the fractions would be over that particular denominator. Now I said a few minutes ago, that's all fine if it's monomials. We just do our prime factorization, and then that same process we have done previously for finding least common multiples. But what if it's not a monomial? What if instead it's a binomial or a trinomial? So this is what we're seeing in example 1b. We have these two expressions, x squared plus 8x plus 15 and x squared plus x minus 6. Now in this case, what you want to start thinking through is not what are the factors of the individual parts of these binomials and trinomials and so on, two trinomials in this case, but instead, what are the factors of the whole trinomial or the whole binomial, depending on what it is. So this is where we go back to that chapter 7-8 skill that we've been working on for months now. What two numbers multiply up to 15 but add up to 8? Those numbers are positive 5 and positive 3. So the factors of x squared plus 8x plus 15 are x plus 5, the binomial, and x plus 3, the binomial. For x squared plus x minus 6, two numbers that multiply up to negative 6 but add up to positive 1. Again, hopefully we've been practicing this for a while now and it makes sense where I'm getting these numbers from. It would end up being x plus 3 and x minus 2. Just like last time, our least common multiple is going to be the product of every individual factor we see. Does not make a difference if it's repeated, used more than once, used just once, if it has a power. None of that makes any difference. Simply identify every unique factor. Here we've got an x plus 5, x plus 3. Again, it makes no difference that we had the x plus 3's multiple times and the x plus 5 just once. I simply list out every individual factor, x plus 5, x plus 3, x minus 2. In this case, nothing has a power, so I don't need to add powers to anything, and that's it. I'm done. I don't even need to multiply that out. We could, if we wanted to, we could multiply it out with Box method, but that's it. That's the least common multiple. If you'll take a quick look at Check Your Progress 1A and 1B, you might take a moment, pause the video, and work through those on your own. See if you can come up with an answer. I will show you how I come up with my answer now. Okay, so hopefully you paused the video and worked this out yourself. 28 m squared n and 12 m squared n cubed p. And we want our LCM. I'm going to do my factorization real quick. This is 2 squared times 7 times n squared, m squared times n. This is 2 squared times 3 times n squared, n cubed, p. So the least common multiple is going to be every individual factor we see, 2, 3, 7, m, n, and p. Again, where I'm underlining this has no significance. I'm just identifying all those factors. I write them down, 2, 3, 7, m, n, p. And then this is going to be a product. Highest powers. 2 squared, 3 to the first, right there. 2 squared, 3 to the first. 7, just 1 7, 7 to the first. M squared happens to be in both of them, I don't care. N cubed, right there. P, just one of them, P to the first, right? And so our least common multiple in this case would be the product of all of this. Now, we don't even have to multiply it out, but we will. 2 squared is 4 times 3 is 12 times 7 is 84. M squared n cubed p. And so there is our LCM. That was Check Your Progress 1A. 1b gives us some trinomials, x squared minus 2x minus 8, and x squared minus 5x minus 14. And we're going to factor these. Two numbers that multiply up to -8 but add up to -2 are -4 and +2. Two numbers that multiply up to -14 add up to -5 are -7, +2. And so our least common multiple is going to end up being the product of every binomial that we see. Looks like we're going to have x minus 4, x minus 7, and x plus 2. And that's that. We don't have to multiply that out. We did when it was easy with the monomials, but we can just leave it in that binomial form. So those are your answers for Check Your Progress 1A and 1B. Now let's use that least common multiple idea to actually come up with some least common denominators. So we're going to do this on example 2. Excuse me. Example 2a has the fractions a plus 1 over a. Notice how I just slip into saying fractions, rational expression, right? But we treat them just like fractions, plus a minus 3 over 3a. Well, as I look at my denominators, although they're not the same, meaning I can't just immediately add them, they are obviously quite similar. The only difference is that if I factored it, this one would be 3 times a. So what I want down here is a 3 times an a. But I can't change the fraction. I can't multiply only the denominator by 3. If I multiply the denominator by 3, I also have to multiply the numerator by 3. So whatever additional factors you see, whether they're simple numbers, or as we'll see in a moment, a whole binomial, even a whole trinomial, whatever they are, if I multiply by that thing in the denominator to get my common denominator, I also have to multiply by that thing in the numerator. Now, once I do that, whatever it is, in this case it's times a binomial, I'm going to have to distribute, right? So this new numerator is 3a plus 3. The new denominator, 3 times a, of course, is 3a. That was the whole point, to have it match that denominator. But the other fraction, since it was already over 3a, I don't need to change at all. That's just going to stay a minus 3 over 3a. And now that I have my common denominator, I do the same thing I always do with a common denominator. My new result, the sum, is simply going to be denominated in 3a's. These are like 3a size slices of pizza. It's my numerator, where I take the sum, right? So 3a's plus 1a makes 4a's. Positive 3 plus negative 3 makes 0. So you can even put the 0 there, but of course it doesn't matter. It's just going to be 4a over 3a. And then just like we did with the fraction I made up a few minutes ago, we want to simplify if we can. Do we have a common factor here on top and bottom? Obviously we do, right? The a's themselves are common factors. They cancel out. And that means this whole expression up here is actually the same thing as 4/3 as long as a is not 0. So remember, we do have an excluded value here. Because my denominator can never be 0, I cannot let a itself here be 0. And so I just note that excluded value. But the expression itself simplifies down to 4/3. Let's do the same thing on example 2b. We've got y minus 2 over y squared plus 4y plus 4. And we're adding that to y minus 2 over y plus 2. All right. First thing I want to do is figure out what my denominators are when I factor them. Notice the fact that my numerators are the same, don't care about at all, right? That makes no difference to me whatsoever. There is no such thing as common numerators when you're adding or subtracting fractions. The y plus 2 is just a binomial. There are no common factors there. There's nothing to factor out, right? So I'm just going to leave that y plus 2. But the y squared plus 4y plus 4, that's a trinomial. That factors. Two numbers that multiply up to 4 but add up to 4, well, that's 2 and 2. Now you might be thinking, wow, there's a lot of y's and 2's, and that's true. But all I care about is making the denominators the same. Are the denominators the same right now? No, they're not the same, right? The imaginary students right now are saying, no, Mr. Ricchuiti, they're not the same. Because I need another y plus 2 over here. So I'm just going to write y plus 2. But can I multiply only the denominator by y plus 2? Imaginary students say, no, Mr. Ricchuiti, you can't. I have to multiply, as always, by a form of 1. That form of 1 will always be whatever I'm multiplying by on bottom, on top as well. Denominator and numerator are always going to match. And of course, we're going to end up distributing here, or using box method. If you need to, you might just jot down box method in the corner. Y minus 2, y plus 2, y squared, positive 2y, negative 2y, and negative 4. When we add all that together, we're going to get y squared minus 4. And so that would be the new numerator up here, y squared minus 4. This fraction did not need to change because it already had the two y plus 2's. So that just stays y minus 2 over y plus 2 times y plus 2. And this denominator here, we have now added everything that we need, y plus 2, y plus 2. And so we're ready to combine the two fractions. Just like we did over here, our denominator is obviously just going to be y plus 2 times y plus 2. But the numerator is going to be the sum. There's nothing to add to the y's. There's no like terms, so I'm going to put that in the middle because that's usually where we put the y term. There's nothing that goes with the y squared, so I'm going to put that first. And then negative 2 minus 4 is negative 6. Sometimes you can simplify these expressions further. In this particular case, we cannot. You can factor it further because there are two numbers that multiply up to negative 6 but add up to 1. Those numbers are positive 3 and negative 2. And our denominator, nothing's changing there, y plus 2, y plus 2. But you'll notice no factors are the same. They look similar, but they're not actually the same, so nothing else cancels. So either one of those two methods, or either one of those two answers, is fine. All right, take a look at the two check your progress problems for number 2. These are on page 608. And I want you to pause the video and try to work them out. So pause. I'm not really paused, I'm blinking. Okay, now it's time. Let's go ahead and take a look at check your progress number 2. You've paused the video. You've tried to work through these yourselves. And I'm going to give you the answers and just very briefly explain how I got there. Check your progress 2a. 4d squared over d, which you'll notice does actually simplify if we wanted it to, but it's not going to be helpful here, plus d over 2 over d squared. Well, obviously the difference is that I need another d in my denominator here, so I'm going to multiply by that over itself, always. 4d squared times d is just 4d cubed over the d squared that we created, plus the original fraction, this one did not have to change, d over 2 over d squared, that's a d, not an l. And so our resulting sum, no like terms on top, 4d cubed plus d plus 2 over that common denominator of d squared. And that's that. Check your progress 2b. I've got b plus 3 over b, and I'm adding that to b minus 5 over b plus 1. Now it's tempting here to say, oh, the difference is that this fraction is missing a plus 1. So if I just add 1 here and add 1 here, then they'll be the same. But remember, coming up with common denominators is not about adding more numbers. If I want to add 5 over 6 plus 1 over 2, I don't say, oh, 1 over 2, if I want to put that over 6, I'm going to add 4 to the denominator. That's really 5 over 6 also. 1 over 2 is not the same as 5 over 6. I can't add to numbers. When I'm doing common denominators, I have to multiply. So I want to think of b as its own factor, b plus 1 as its own special factor. Although they look similar, otherwise they have nothing to do with each other. They just happen to use the same variable. What's the one that I need over here? I need the factor b. But if I'm going to multiply the denominator by b, I also have to multiply the numerator by b. What's the factor I need over here? B plus 1. But if I'm going to multiply the denominator by b plus 1, I also have to multiply the numerator by b plus 1. And of course, I want to be careful. I want to remember both of these are binomials, so I have to treat them that way when I multiply stuff out. I'm not going to show you the box method here, but that's what you would use to multiply out that numerator if you need to. You're going to end up with b squared plus 4b plus 3 for that first fraction. Over here, we don't have to use box method. We can just do our distribution. And so we're going to end up with b squared minus 5b. And the whole thing, of course, is over our common denominator, which we could expand out if we want, but we don't have to. We can just rewrite it as b plus 1 over b. And again, if we can cancel it all at the end, it's useful to have kept our denominator in factored form. Let's add together what we can. B squared plus b squared is 2b squared. 4b plus negative 5b is minus 1b or plus negative 1b, however you want to phrase it. 3 plus nothing is just going to be 3. And then the whole thing is over that same common denominator, b plus 1 times b. This numerator, you might think trinomial, maybe we can factor it. Remember, when you have that coefficient there, we do a times c. 2 times 3 is 6. So we want two numbers that multiply up to 6 but add up to negative 1 if we were going to factor this. And in fact, there are no such numbers, right? There are no two numbers that multiply up to negative 6. No, I'm sorry, positive 6 and add up to negative 1. And so we can say, actually, that numerator is not factorable. And so this is the final form. Again, if you wanted to multiply out that denominator, you could. So we could also call this 2b squared minus b plus 3 over my distributed denominator, b squared plus b, but there's no reason I have to do that. Either one of these two answers is acceptable. All right, one more example. We're going to find a difference this time, so we're going to do some subtraction on example 3, and then this lesson is done. And at that point, hopefully, you are now a master of adding and subtracting rational expressions with unlike denominators. So, example 3a. We've got the rational expression 4 over 3a minus 6, and we are subtracting a over a plus 2. These denominators definitely look different, so I'm going to factor them and then see if I have any common factors, what my LCM is, etc. This one, for example, I can pull a 3 out of, but it leaves an a minus 2. There's nothing else to factor. That numerator stays 4. That numerator stays a. That denominator stays a plus 2. Anytime this happens where you have no common factors whatsoever, your least common multiple just has to be the product of everything. So I'm just going to make sure each one of these three factors is represented in my denominators. This one obviously has 2 of the factors because that's where it came from. That's what we started with. But it's missing the a plus 2. So I'm going to multiply by an a plus 2. And if I do that in the denominator, I'm also going to do it in the numerator. This one is missing both of these 2 factors. Again, we said there was nothing in common. So I need a 3, and I need an a minus 2. And again, if I do that in the denominator, I'm also going to do that in the numerator. I want to remember these are binomials, so I'm going to use some parentheses here to remind myself of that. I have to be careful when I multiply using box method. But up here I get to do some simple distribution, no box method, because this is just a 4, obviously. So I get 4a plus 8, and the whole thing is over that common denominator, which again, I don't even need to multiply out. I am going to rearrange a little bit, just because we usually put the numbers in front. And I am subtracting, and I'm going to have that same denominator, because again, that's the whole point. I'm getting that common denominator. My numerator, though, 3 times a is 3a, and so it's the 3a that I'll be distributing here. 3a times a is 3a squared. 3a times negative 2 is minus 6a. And now I'm just going to go ahead and do my subtraction. Nothing, for example, I'm doing my 3a squared first. Nothing minus 3a squared is negative 3a squared. 4a minus negative 6a is plus 10a. 8 minus nothing is 8. And of course my denominator is going to be that same expression, 3 times a plus 2 times a minus 2. And again, at this point, presuming that's in most simplified form, we're done. That's the answer. Now I don't know this is in most simplified form. I might come up here and try to factor this. Remember, we've got a coefficient. So negative 3 times 8 is negative 24. Are there two numbers that multiply up to negative 24 but add up to 10? The answer turns out to be yes, unfortunately. So what I might do is drop this into box method real quick. Negative 3a squared plus 8. What two numbers multiply up to negative 24 but add up to 10? Positive 12 and negative 2. And so that's what I would fill in on my box. I've got a negative a in common here. Obviously I must be multiplying by 3a to get negative 3a squared, which means I must be multiplying by 4 here, negative 2 here, and then negative 2 times 4, negative a times positive 2. There we go. Negative a times no. What's going wrong? Negative a. Yeah, never mind. Negative a times positive 2 is negative 2a. 4 times 2, also 8. And so that numerator factors as 3a plus 2 times negative a plus 4. But at this point, I can see it does not share any factors in common with that denominator. And so I actually can't cancel anything out. And again, either of those two answers is fine. For example 3b, if you need to copy this down, pause the video. Okay, so you've copied it down by now if you wanted to copy it down. Let's get example 3b up here. Same exact concept though, we're just taking a difference. We've got h minus 2 over h squared plus 4h plus 4, and we're subtracting h minus 4 over h squared minus 4. A lot of things look similar here, but again, we're not looking for similarities, we're looking for factors. So let's factor everything we can factor. This is h plus 2, h plus 2. This binomial, remember that's a difference of squares pattern. That's h minus 2, h plus 2. If that does not make sense, you need to go back to chapter 8 and look up difference of squares. Our numerators don't have anything to factor, so we're just going to leave those alone. They also don't have anything that will cancel. We don't cancel across subtraction or addition. We can only cancel across regular division or multiplication. All right, h plus 2, we have that in common, but this one has a second h plus 2 that this one does not have, so I'm going to multiply that in, and of course if I do it on bottom, I do it on top. And clearly this one has an h minus 2 that this one does not have. So I'm going to multiply that in, h minus 2, h minus 2. Again, I've got some binomials, so I put parentheses around to remind myself to properly multiply that out. Use box method if you're having trouble multiplying that out. But you should get h squared minus 4h plus 4. And here, you're going to end up with h squared minus 2h minus 8. And the whole thing is over our common denominator, which I'm going to abbreviate a little bit. I'm just going to write it as h minus 2 times h plus 2 squared, because I used 2 of the h plus 2 factors. So that's what that ends up looking like. From here, we want to do our subtraction. H squared minus h squared is 0 h squared, which we don't need to write down. It's just nothing. Negative 4h minus negative 2h minus a negative. Remember, we're really adding. Negative 4 plus 2 ends up being negative 2h. 4 minus negative 8 plus 12. And of course, my common denominator, nothing is changing there. H minus 2 times h plus 2 squared. Negative 2h plus 12. Sorry, I need to check something. Good, sound is working. That would have been unfortunate. Negative 2h plus 12 does actually factor, but you can quickly see when you pull that negative 2 out, it doesn't factor usefully. So again, either of these two answers is fine, whether you do factored form or the unfactored form, or if you wanted to multiply out your denominator, all of that would work. So last two, check your progress problems. You can, oh my gosh, there are 4 of them. And maybe I'll just let you figure those out on your own. So that has been adding and subtracting rational expressions with unlike denominators. Find your least common denominators, multiply out in terms of forms of 1, add and subtract as is necessary, get your answers, simplify if you can. Good luck.